Good evening. Thanks for joining tonight's TI Technology webinar hosted by Texas Instruments, where tonight we're going to go beyond the basics with the TI-84, specifically looking at Algebra 1 and Algebra 2. My name is Mike Houston. I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI Technology to make those really tough to teach and tough to learn concepts accessible to all my students. And I'm excited to be joined by our two panelists tonight, David Sword and Leo Zambito. These guys both come with a lot of experience. Dave has worked as a national instructor for TCUBE for over 20 years. He just retired in June. Congratulations, Dave, from Wayne Regional Educational Service Agency in Wayne County, Michigan, where he worked as a math consultant since 2009. In his role at Wayne, Dave trained and deployed math coaches in priority schools, planned and provided professional learning for teachers and school leaders, and provides support to 32 school districts and more than 100 public school academies in implementing local, statewide, and national initiatives. And since 2004, Dave's been an adjunct faculty member at Wayne State University in Detroit. Previously, he was a high school math teacher for over 20 years, mostly in those Detroit public school area. He's also been a part of several writing teams at TI and pilot projects for TI, mainly TI Navigator, TI-Nspire, and TI-Nspire Navigator. So Dave, it's great to have you with us.
Thanks.
And Leo has been teaching high school math since 2008. He is currently the department head of math at Father Bressani High School in Ontario. He teaches AP Pre-Calculus and AP Calculus, and he uses technology in his classroom to facilitate learning daily. So Leo, it's great to have you with us as well.
Thanks.
All right, Leo, what are we going to do tonight?
All right, we got a lot of wonderful things on the list here for tonight. So we got our welcomes and introductions done, but we are going to be discussing fixed mindset versus growth mindset in calculator pedagogy. And this is big because we're using the calculator just for so much more than just the things that we commonly would use it for. So Dave's going to talk about that. We have we're going to use the home screen and list operations to symbolically and recursively discover and understand linear and exponential patterns. There's a lot of functions hidden in the calculator that you can do on the home screen, and Dave's going to show you some of those coming up soon. I'm going to show you how to analyze some polynomial functions and just the usual things, but just being able to use it, analyze them graphically, but also on the home screen. We're going to dip into the polynomial solver. We'll look at the numerical solver app, and then we're going to go into combining functions. We're going to use a piecewise function built into the calculator. I'll show you how to combine different functions graphically and analyze them in the tables. We're going to use list computations and function tables to explore transformations of functions. And then we'll apply some piecewise functions and transformations of functions to solve some real world problems. Stick around at the end. We do have a free TI-84 graphing calculator that we are going to give away, I believe.
Yeah, it's actually a graphing calculator of their choice. So if they want the 84, they could have that. If they want the Nspire, they could have that. But yeah, stick around to the end for that. Thanks, Leo. And David, what can we expect to be able to know and be able to do by the end of the webinar?
Yeah, hopefully by the end of this, folks will feel comfortable saying that I can promote a calculator-based growth mindset, student thinking about mathematics. Hopefully you'll be able to say that I can use advanced features of the TI-84 Plus as a tool for discovery and inquiry. And I can use the TI-84 Plus to solve real-world problems.
Thanks, Dave. So tonight, I think I looked over what Leo and Dave were going to be sharing tonight, and I already have my pen and paper handy because I'm going to be marking down kind of some things that I'm probably going to need to look back and watch again with the recording. So as a reminder, the session is being recorded, and we'll provide a link to the event certificate of attendance, as well as a link for the documents that Leo and Dave are using at the end of the webinar. So stick around for that. We also are going to be using that chat window tonight. I know many people have already sent us hellos from where they're joining us from, and that's a personal favorite of mine. So thanks to everyone that did that. And without further ado, David, it's all yours.
Thanks, Mike. So I'd like to welcome you and let you know that we're going to cover a lot of things tonight. And so what I'm hoping is that you'll like Mike said, that you'll have some notes with you and ready to write some things down as we go. If you have your calculator and or your emulator, you can try some of the things as we're going along. If you're unable to keep up, don't worry, because this is recorded and you can watch it again and move at your own pace as you watch the recording. But without any further ado, I'm just going to get right into it. And so here we go. The first thing that we want to talk about is a fixed versus a growth mindset in using calculators. There's lots of reasons that people use graphing calculators, and some are good and some are better than others. One of the things that we like to talk about, though, is there are some reasons that are somewhat limiting that a lot of people lean towards, and we want to realize that there's more to the calculator than that. For example, some will say, yeah, you can do things on the calculator that you can't do by hand. So the calculator is a really good tool for that. And that's what I call efficiency. So while that's important, there are better reasons than that. For another thing that people often say is the calculator doesn't make any computational errors. So that's a good reason to use a calculator. And so accuracy is a good reason. While that's true, I believe that there are better reasons, and that's what we want to talk about tonight. And then another that people often use is that you can use the calculator to check your work. And so I call that confirmation. But again, there's so much more to the calculator than this. And so that's what we want to focus on tonight is a growth mindset and ways that we can use the calculator as a tool to help support learning, growth, and exploration. For example, one of the things that we can let kids do is to play around with math ideas and to observe and recognize patterns. And so we're using it now as a tool for exploration and discovery. Another thing that we can do is use the calculator to explain some of the why, to help students understand mathematics. We're going to look at that in particular tonight about transformations of functions. And so that's a growth mindset a reason for using calculators. And then the two that created this group that we call T-Cube, teachers teaching with teaching with technology, Bert Waits and Frank DeManna coined the phrase the power of visualization. And it just, by that, what they meant was when we use the graphing calculator and see the tools and being able to visualize the mathematics, there's a real power in that. And so one of the things that I like to talk about is how this then connects to these three ideas here of symbolic manipulation, symbolic representation, and symbolic interpretation. One huge role of the calculator is in supporting these areas. But let's talk about them for just a second. Difficulty level for students. Well, first of all, what do I mean by symbolic manipulation? I mean solving equations, simplifying expressions, things that are typically done without a calculator, right? But symbolic representation is where we can take a math situation and use symbols to represent that situation. And then interpretation is taking the math symbols and then making sense of how those symbols fit into the context of the mathematics or a real world problem. But difficulty level for symbolic manipulation is typically pretty easy, but it can be hard depending on what you're asking the students to manipulate. But the representation it gets harder. It's harder to teach, harder for kids to understand, and symbolic interpretation likewise is harder to understand, harder to teach. And so along those lines, the teaching of it's easy to teach symbolic manipulation, but harder to teach representation and interpretation. But then when we get to the cognitive demand level of our students, it's pretty low cognitive demand to focus on symbolic manipulation, even though it's important. I'm not saying it's not important. What I'm saying is it's typically kind of a low cognitive demand, whereas representation and interpretation are high. And then the benefit to students, unfortunately, symbolic manipulation is low to medium. It's important, right? But there are mathematical benefits to representation and interpretation that are much higher. And here's the killer to me is the time that we spend. It seems to me, in my experience, we spend a lot of time on symbolic manipulation, but very little time on representation and interpretation. And these two areas are where the calculator can be a really, really, really powerful tool. Let me illustrate that by taking a minute and looking at some samples of just looking at the home screen as it relates to linear functions, okay? So there's lots of things that we can do on the home screen, but one of them just relates to using the home screen as a tool for looking at patterns. Okay, I can hit 1, enter, right? And I'm sure that you know that down here above the negative sign, there's a button called ants. Well, that ants means the last answer. So if I hit second ants, that pulls up the last thing that I did, which is that 1. But one thing that's really cool is I can just hit the +1 and it just automatically takes that last answer and adds 1 to it. And then if I hit enter, 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 I've just kind of enter that sequence in there that helps me look recursively at this linear function. And I can see that linear functions are those things that change by a constant rate. You know, I can do something like this. Let's start at, say, 5. And then if I want to add 2 to each one of those, I'm just going to hit +2. And it shows ants 2. And so there I go, 7, 9, 11, 13, 14, 15, so on. So I can see with sequences and series, I can see how a linear function changes. I can take something like 1, enter, and then I can say, well, a minute ago I was looking at how they change by addition. Well, what if I change it by multiplication? What if I multiply by 2 each time? I start to see, oh my goodness, there is a quadratic sequence. And so it's just using the home screen just as a tool for exploration. Here the students can see how the patterns change, linear, exponential, and they're actually starting to recognize some symbolic representation. That ants was the previous answer. But we can even take this environment here and beef it up a little bit more by using a set. So if I use the braces, the second above the parentheses here, and if I just hit, like, say 1, 2 and close that brace, I'm entering a list here on the home screen, okay? But symbolically, this answer right here, if I hit ants, it's going to pull up those 2. But the thing is, there are 2 of them here. So the 1 is ants 1 and the 2 is ants 2. So I could actually do this, second ants, parentheses 1, and the calculator knows that ants 1 has a value of 2 right now. Excuse me, has a value of 1. So if I hit enter, there's that ants 1. So if I go back up here and grab that 1, 2 again, let me try that again. Sorry, enter. I don't know why it's not pasting that down. That's why. Let me go grab this one. There we go, sorry. And I'm going to paste that down. And if I do ants 2, I can see that that's refers to the 2. Now, you might not think that that's all that spectacular right now, but when it gets really cool is when you do something like this. Let's just say I'm going to set up a set with, say, 0 and 1 as the 2 members of my set. And what I'd like to do is I'd like to look at how the patterns change here. I'm going to take ants 1, that 0, and I'm going to just add 1 to it. But then take this 1 and I'm going to square it and see what happens, like with a quadratic function. So how can I do that on the calculator? I can take that ants 1 and put it in this set, and I can take ants 2, sorry, what am I going to do to ants 1? I'm going to increment that ants 1 by 1 so that it'll kind of function as like my counter. So that 0 right now is going to count by 1s. Now let me take ants 2 and let's see what happens if I just say square that. Well, nothing's going to happen, right? Because it's a 1. How about if how about if I say, because if I square 1, that wasn't a very good example, was it?
Maybe double.
Sorry, folks. Let me change that squaring. Whoops. To timesing by 2. Let's try that. Let me get rid of that exponent. Oh my word, that's embarrassing. Delete that thing, delete that, and close the braces, right? Now let's just make sense of what's happening here. I have ANS1, which is the 0, and I'm going to be incrementing it by 1. I have ANS2, which is the 1, and I'm going to be multiplying it by 2 each time. So let's see what happens. I get 1, 2, I get 2, 4, 3, 8, 4, 16, 5, 32, and so on. So it's just a really, really powerful way that students can start getting practice with symbolic representation, symbolic interpretation, and looking at how those patterns are changing both in linear and exponential patterns. I could even do this with a list of 3 items. It just kind of gets really clunky if I had, say, let's just go 0, comma, 1, comma, 1. You know, I could do the same thing. And we have a picture of this in our PowerPoint that you can download just so that you can see that you can do this even comparing linear with exponential. Let's just do that real quick. I'm going to take ANS1 and I'm going to increment it by 1. I'm going to take ANS2 and let's just say, let's multiply it by, let's do this. Let's add 3 and look what a linear function looks like compared to an exponential function, ANS3, that's going to be multiplying by 2. All right, so here I can see now there's that linear function that's increasing by 3s. I can see that the exponential function is doubling. And so I'm using the home screen to compare what happens in the change for linear functions versus exponential functions. So that's that recursive approach to next the start value and how much it's changing by. And for just one last way that we can explore this similar concept is to do it in the stat editor with lists. I can put a list in list 1, let's just say 0 up to 10. And there's a variety of ways to do this. A lot of people like to use the sequence command to put a list in there. That would be a nice thing for you to investigate. It's not something that we had planned on talking about in this webinar, but using the sequence command is a nice way to get a list of numbers in this column. But here I can say, what if I did second L1 and I'm going to add, say, 3 and see what happens. And there I can see the change that's happening in linear functions. I can see that they're going up by that constant difference. In fact, I can even explore that a little further by using the list command. And I see that in operation number 7 is delta list. If I look at delta list of list 2, I can see that each of these is changing by a constant amount. And so using those constant differences help me explore the relationship of linear functions. I can even expand this to look at quadratic functions. If I put L1 squared in list 2, now I get a quadratic function. And when I come over here and look at the consecutive differences by using that list command, I go to operations, list of L2, and I see that it's not constant. But when I go to the second differences, I look at second stat, operations 7, which is delta list of L3. I can see in L3, oh, these have constant differences. So it helps me see that quadratic functions change by a constant difference. The other way to compare that then is to see what happens with exponential functions. Whoops, I want to clear that. I want to clear this. And I want to clear this. So when I go back to list 2, if I did this one as an exponential and I did, oops, say 2 to the L1, and I see I get that exponential function here. This is really cool. Let's look at the constant differences here. When I go to stat, delta list, and I look at these constant differences, something really, really cool happens unexpectedly. Oh my goodness, it gets repeated. And so there's some different kind of a change going on here. So this is really cool for so many reasons. This is Algebra 1, this webinar, but this is also connects to calculus. The derivative of an exponential function is an exponential function. And so there's some really, really cool calculus going on here, but it starts though in the same environment here where we're exploring these changes. How are things changing term by term? And then as we continue that exploration, we see that it happens with exponential functions in a different way. What's happening in exponential functions is this 2 divided by 1. If I take 2 divided by 1, instead of 2 minus 1, I'm going to take 2 divided by 1. Instead of taking the difference term by term going backwards, I'm going to take the ratio term by term, and I see that that's a 2. When I take 4 divided by 2, 4 divided by 2 is also, hey, look at that. And so 8 divided by 4. So we see that there is a different kind of a change, that term by term, that recursive change that happens in exponential functions is a common ratio. And so it's a way that we can help students understand that concept and explore that concept. And I realize tonight in the context of this webinar, this is something that we're kind of going through pretty fast. Please forgive us for that. But what we're trying to do is show you a way that you can kind of use this as a tool for exploration with your students. And you can kind of slow that process down and take your time and really explore that. But we wanted to give you the opportunity to see a variety of approaches that you can use to explore this concept. And I'm just going to show you one last thing before I turn it over to Leo, and that is one of the nice things that you can do is capture this repetitive action here. I'm just taking the L2 n plus 1 divided by L2 of n. I'm just repeatedly doing that. Like down here, this is L2 9 divided by L2 8. So it's always L2 of n plus 1 divided by L2 of n. I just have a little program. You can write this as a program. It's really cool. This program is just 3 lines long. I just wanted you to see that program. Whoops, edit it. It's I used A instead of N. Forgive me for that. I said N a minute ago, but here we're using A in the program. But it's just a loop for 1 up to the dimension of L2 means how long list 2 is. If there are 10 items in list 2, there are only 9 ratios. So I do for A equals 1 up to 1 less than the dimension. So that's what this statement is saying. And what does it do repeatedly? It just takes L2 of A plus 1 divided by L2 of A and puts that into the list 3 of A. And so you can see right here how that program works. If I just say program TI basic, number 1, and I go to ratios and I run that program, it says done. But now when I go to stat edit, there all of those 2's are populated because that program just went through and did all of those ratio calculations. So again, it's a way that you can help students in their application and their understanding of symbolic representation, symbolic interpretation, as they look at sequences and series and recursive changes with linear and exponential functions. So with that, I'm going to turn it over to Leo, and Leo's going to do some work with you. Go ahead, Leo.
Thanks, Dave. I really love how you showed that programming at the end. I mean, over here, we're encouraged to start showing students how to do some simple programming and simple
Where is here, Leo? Did you say that before?
Here in Toronto area in Canada, they actually embedded coding for us not too long ago in grade 9, and it's like everyone's getting scared. Oh my God, coding! It's like, no, guys, it's not that bad. It's just a sequence of mathematical operations. It's not that bad. So that's a great way to, I think, introduce students to some coding there, just right on the handheld. Can you see my screen there?
Not yet.
Not yet. All right, let me push the right button, not the left button.
There you go.
All right, so
yep.
Just to kind of piggyback on what Dave was doing, I think patterning and in mathematics is just crucial. It's super important to explore, and I love how you can do it so efficiently with the TI-84. And it really is the pre-calculus. When you start talking about first differences and second differences, you're getting into rates of change. And my students sometimes get all panicky when calculus is coming up. Oh my goodness, calculus. It's like, guys, it's just a change in functions and patterns that we're looking at and how things change. And so it's a perfect segue into calculus when you can do that, and being able to do it with the list so efficiently, I think is very vital to be able to help students explore efficiently and support their understanding of those patterns when comparing the different functions. So going on to some other functions, what I want to do now is take some time to look at a polynomial function and just go over how to use the TI to evaluate it and how to solve equations. Polynomial functions come up everywhere, even in rational functions. It's just a ratio of polynomial functions. So let's start with something like this. We're gonna go to the equations menu here, y equals, and I have this equation already entered, but it's x cubed minus 6x squared plus 9x, and I'm going to graph this. Now, the visualization here is students, if you're plotting equations, it's like after a while, some students finally get it, and it's like they have an aha moment. What is an equation when you graph it? It's a collection of points. And so on the graph menu here, if you hit the trace button, you can go through, traverse through the graph and see the collection of points. And how many points does it take to make a curve? Well, my answer to that is infinite. It really depends on how precise you're being. How many pixels does your screen have? How many dots are you willing to draw on a piece of paper? We're intuitive as humans, and we'll connect points using a line or a curve, but really it's just a whole bunch of little points, little dots that satisfy the equation. Now, when we're working with polynomials and other equations, and we're exploring, what does this equation spit out if I input the value 1 for x? A lot of my students will reach for the trace button and then try to traverse to where x is 1, and you'll see that it'll get pretty close. And this is the limitation of the trace feature. It doesn't always snap to the values you want it to. So right now it's at x is 1.06. So how do we get it to go right to precisely x is 1? Well, we can use the calc menu. So if we go over here to the second function, trace, and a lot of wonderful things in this list here. We're going to explore some of these today, but let's look at the first one here. We call value. If I call x is 1, and it'll snap right to that point. So when the input is 1, we have the output 4. And of course, we can do this numerous times. We could do it more efficiently if we look at the table of values. So if we hit the second function key and go to the graph button, that'll get us to the table of values, and we can see there's that point we just found, 1, 4. But what if we wanted to go at, let's say, x is 1.5? Well, we could do that using the value feature under the calc menu. There it is, 1.5, but it's not in the table. You'll see the x's are going up by ones, and I know some of you, I'm sure, already are aware of this, but we can set what the table starts at and what it increments by. So under the, right here above the window key, you have the table set function. Let's say we want to start at 0, start the table at x is 0, and we'll go up by 0.5s. And when we get to the table there, we'll have 1.5 is right there. And that's great. So we can get values from an equation on the graph. We can get it from the table, but we can also get it from the home screen. And this is one of my favorite features of the calculator. So on the home screen, we have that equation entered in as y1. And what I'm going to do is call it. Now, the shortcut menus, if you haven't used these already, if you hit the alpha key, you'll see at the top says F1, F2, F3, F4. F4 will bring up all your equations. There's some great shortcuts under the fraction menu. I'll use those later, converting between fractions and decimals, and a lot of wonderful stuff under the functions menu. But let's just focus on the variables for now. The y variables. I'm going to call y1 at, I'm going to use function notation here. I'm going to call y1 at 1. So I can get the point there. And I saw some of you talking about the copy and paste feature in the chat. That's like my favorite feature. Just go on up, highlight it, hit enter, and we can just call y1 at 2 or even 3. And the other part is if we wanted to evaluate it at maybe more, maybe inputs that involve decimals, well, yeah, I can call y1 at 1.5 or 1 point, whatever I like. And I don't think you even need to close the bracket. So you could just do open bracket and then the value. So you don't have to close it. Okay, so we can evaluate a function on the graph page. We can evaluate it from the table. We can call it on the home screen. Awesome. But what about solving equations? That is probably a barrier algebraically for many students. So let's look at how we can solve an equation. One of the points we are usually interested in finding is when a function equals 0. So what I'm going to do is just graph the line y equals 0. And I do this almost always when I'm showing my students things on the graph, because for a couple reasons. Number one, it highlights the x-axis, which is great. I think it's just easy to see it, especially with the color coding and you have it there in red. And the other reason, if I want to know when it equals 0, I can see here that there's probably two answers. There's one here on the origin, and there's one down here at x is 3. So to get those answers, I have two options. I can go to the calc menu, and I can use the 0 feature. The 0 feature, option 2, is going to find when the graph or this function crosses or hits the x-axis. Now to do it, it's going to ask for the left bound. So we do have to go before it crosses the x-axis, and then the right bound. So you do need to set the bounds where the cross happens. When is it hitting 0, before and after? And then you need a guess. So you got to direct it to the middle. And it gets me the answer. That's great. It took a few clicks to do it though, because I do have to get before and after and then guess. But if you have the line y equals 0 graphed, you can just use the intersect option. And that's the one I usually go to whenever I'm solving equations graphically. So what you'll have to do is pick two curves. You'll see up here, the first one is the polynomial. And the second one is my line, y equals 0. And if you did have multiple equations entered, you could just use the arrow keys to traverse through the different equations. So I want y1 and y2. And now I just have to guess. So I can just drag the cursor along this red line to where it hits 0. And if I hit enter, I'll get one answer. And if I try it again, intersect equation 1 and 2, If I drag it closer to this other spot, should get that guy. I know it keeps snapping back. Maybe it doesn't actually hit 0. Let's check the table. 3, nope, it does. Maybe we'll have to do a little zoom in at that point. Try and zoom in. There. Looks like it's hidden there. We'll try one more time. Intersect. Equation 1 and 2. And my guess. And there it is. So to 3 decimal places, it's going to be at x is 3. Now, let's zoom back to standard and look at how else could we solve this equation. Well, you can't solve it from the home screen, but we do have a couple applications built onto the calculator that will solve equations a lot more, maybe efficiently than you would on a graph. So the first one I wanted to show you under the math menu is right at the bottom. It's the numerical solver. Now, the numerical solver is something that I use regularly, especially when you're dealing with linear equations. I think it works really well with linear equations and equations where one answer is expected, because it does spit out only one answer at a time. So if we take an equation like this line, 2x minus 1, and we want to know when it equals 5, we can hit OK. Remember that when you're in apps, these buttons or these labels down here are linked to these F1 to F5 buttons here. So when you use the solver, you do whatever you type in here for x. It's sort of like you're directing it to look there. You're giving it like a guess to solve it close to there. So at this point, it gives me, if I hit solve, the answer is 3. We can see 2 times 3 minus 1 is in fact 5. And that's great. But what if there is two answers? So let's go back to the solver. And I'm going to type in the polynomial that we had, which was x cubed minus, I'll change that to a cube, minus 6x squared plus 9x. And we were interested in knowing when it equaled 0. So if I hit OK and solve, so it got us one answer, x is 3. Now, if I go back to the table of values, you can see that, yeah, that was one of the answers. When x is 3, the equation equaled 0. What about this other answer here? Why didn't that one pop up? So it's all about directing the solver towards that answer. And this is sort of the limitations with the solver. If I want to get that other answer, I'm going to have to direct it closer to there, even on the minus side. Or I could even restrict the bounds. I could say, give me the answers, but from negative infinity up to 0. If I do that and give it a guess, then it'll actually get the answer 0. If you do this with trig functions like sine, sinusoidals, it will give you all the answers you need, but you do have to direct it where to look, which is why for polynomials, tend to steer towards the polynomial solver app. So if we go to the apps screen, you'll see it's listed number 9 here. Probably one of my favorite apps on the calc, or at least my students' favorite app. They're always reaching for the polynomial solver. And you can use it to solve multiple equations, but we're going to go with the first option here, root solver. And we're going to choose order 3 because it is cubic. And for those of you who dive into imaginary numbers and complex numbers, it does have the options there of spitting out the complex solutions, like polynomial x cubed minus 1 only has one answer. But if you did turn that on, you could get the imaginary numbers too. But I'm going to stick with just real numbers. So I'm going to go next, and I'm going to type in our polynomial 1x cubed minus 6. Now, a little tip here, you can change the signs, but I usually do keep them all positive. And what I do is just change the coefficient to be negative. If I do want to have minus 6x squared, I'll just put a coefficient of negative 6, then plus 9x. And the constant at the end for this polynomial is 0. And if I hit solve, we get 3 answers, but 2 of them are repeated. And this can sort of segue into the conversation about the fundamental theorem of algebra. Every polynomial of n degree must have n solutions. So this one does have 3 solutions there, but 2 are twice. So it does hit the answer 0 twice. But now let's say we wanted to solve a more complicated equation. Let's consider for a moment, when did this polynomial equal 2? So if we go to the graph, we can see that it's going to hit 2 3 times. And a couple of them don't look like they're going to be very pretty answers. One's 0 point something and one's about 3 point something. So on the polynomial solver app, I'm going to jump back to that. And I'm going to change the equation now. We want to know when this polynomial equals 2. However, it's a root solver. It can't solve for a polynomial equal to anything except 0. So now it comes to a little bit of conversation about how can we manipulate this polynomial to find out when it equals 2. Well, if it's going to be equal to 2, let's subtract 2 from both sides, and that'll be equivalent to solving this equation. And if we solve that, we get our 3 answers. Now, a couple cool things about the polynomial solver app. You can store the equation to your y equals menu. You can also store coefficients. I'm going to use the store feature now because I find this really useful. So let's say you started with the polynomial solver and then you wanted to explore graphically. All you got to do is hit that store button, go down to the store polynomial to y equals option, and it'll store the polynomial to the next empty equation slot. So if we go back to the y equals menu, you'll see that it just put that equation in for us. X cubed minus 6x squared plus 9x minus 2. Great. Now we can look at it graphically and we can have some conversations here, because what we were solving was when the polynomial equaled 2, that's when the blue curve hits the green line. But what we did was manipulated the equation by translating it down 2 units, and it's equivalent to finding when that pink curve equals 0. Hey, that's why we use that whole factoring technique, right? Why do we subtract from both sides to get one side equal to 0? It's all about manipulating to make a harder problem easier to work with. So I love how you can kind of compare that, and just how we didn't have to retype it. It's all there. All right, let's look at some other things we could do. I think that's it for the equation solving and polynomial parts of things. What we did want to dive into a bit now is a little combining functions and piecewise. How am I doing for time?
You're doing good.
Okay, so let's just quickly do, we'll do this. We'll keep this original polynomial. Let's add in another function, something easier to work with. We'll add a linear function. We'll do 4 minus x. And if we graph them, we have that polynomial and we have a linear function. Great. We can combine these in so many different ways. So first of all, let's jump to the home screen. We have, actually, before we do that, let's do this. Under y3, so when you combine functions, we can add them, we can subtract them, multiply, divide them. We can plug one into the other and make a composite, or we can combine them in pieces. So let's look at how we can combine these by adding them. And then you could do this, you can use the same technique for multiplying and dividing. So to call y1 and y, instead of retyping them, because that's tedious, let's go to that shortcut menu where we can call our equations. So I'm going to do y1 plus y2. And if I graph it, we get a new curve. And that curve is a combination of the red and blue. Basically, and we can kind of analyze now. We could do some exploration. We can go to the table and see, well, how did that come about? Why did that green curve, why did it end up higher up on the screen? Why are the points higher up? Well, it's just an addition that we use. We're just adding the y values to produce a new output. There's a combination of the previous two. So you can see the pattern in that list. Well, what about rational functions, right? Well, let's take the fraction template here. For those of you who don't know, it's right above the variable key. And I'm going to do the polynomial over the linear. That way there's only one asymptote. So we'll do y1 over y2. And I want to compare now how these first two relate to this equation here. But what I don't want to do is have this one show up. So I'm going to hover over top of this y equals, y3 equals. I'm going to hit enter. When you unhighlight an equal sign, that won't show up on the graph anymore. So what we're going to have in the table and in the graph is the first two and the rational function. So here's the graph. And then here's the table. And we can see how the pink entries are a ratio of the two. And then this one's an interesting one, right? Why do we get an error? Well, 4 divided by 0 is undefined, right? Lastly, just quickly before I jump to doing some things from the home screen, is you'll notice some of these are decimals. I'm going to set the table to go up by ones here. And if we look at the table, you'll see these fractions now? Because I'm going up by ones, whole numbers, it'll actually divide consecutive y values and produce the fractions. But let's say you did want the decimal outputs as well. Instead of 4/3, we'd like to see maybe 1.333. So what you can do is go down here to y5. We'll call up y4. And if you multiply it by just 1.0, you'll get this popping up. So now you can get the fraction, the rational numbers, but also their decimal equivalent, which is, I think, is great to support that understanding of why those rational functions produce certain outputs, and just the understanding that it helps facilitate with the decimals. Okay, last thing, because I know I'm running short on time here. We're going to do on the home screen. Actually, I will show the piecewise function, but let's do this from the home screen really quick. We did have the y1 and y2, so just know that on the home screen you can call these functions as well. So let's say we wanted to do a y1 divided by y2. Now remember, you have to use function notation on the home screen. So if I'm going to call y1, I need an input. So I'm going to call y1 at 1, for example, and I could call y2 at 1. And so I can see how those two functions produce that ratio. I showed you before, or I mentioned before, the shortcut menu for the fractions. I really love option 4 here. That will allow us to convert an output to decimal. And of course, we can do things like just add y1s or y1 at 2 minus y2 at 2. Take differences, take sums. So definitely explore those on the home screen. I think that's very valuable. Okay, last thing, because I got to turn it over to Dave in a second. The piecewise. Many people don't know that this feature is buried in here, but if you go to the math menu, down to where the numerical solver was, right above it, it says piecewise. So what I'm going to do here is insert a two-piece function. Now, the first one, I'm going to use polynomial y1, and the second one, I want polynomial y2. Now we have to set some domain for each of these. So I want y1 to show up for certain inputs. So I'm going to have y1 show up for all the x values less than 2. So where are the less than, greater than symbols? They're actually all under the test menu. Test. Where are you, test? There it is. Math key. Second function, math. And that's where you'll get your logical test values. So we're going to want that to show up for all x's less than 2. And then we want the linear equation to show up for all x's greater than or equal to 2. And if we graph it, you'll see the green is just really the polynomial up to 2, and then the line takes over after 2. And you can hide the other 2 and just have the piecewise show up, which I think is great. All right. I think that's it for me. How are we doing for time?
We're doing good.
Okay, I think the only last thing probably worth showing is the composite really quick. If you wanted to, you could plug functions into other functions. So you can do something like this. And basically what that's going to give you is evaluating y2 at 3 and then plugging that into y1, and you get those composites showing up, and you could graph them if you wanted to. All right, I'm going to turn it over to Dave before we're completely out of time. It's all yours.
One of the final things that we wanted to talk about, and I know our time is short, so I don't want to rush because I felt like I was rushing a little bit earlier. But one of the really powerful uses of the calculator is in helping students understand. In fact, one of the most frustrating things that I've often struggled teaching is, why does a function f of x minus 3 shift to the right and not to the left? Students see this minus right here, and they think that this is going to shift to the left, but we have to try to teach them that it shifts to the right instead. And why does that do that, right? It's really, really hard to teach to students. One of the nice ways to teach it to students is this way. If I go into my list editor like I did earlier, look down at the bottom here. I just typed some function. It doesn't matter what I typed. I just happen to type 2 times L minus 1, and it produces this list over here, 2, 4, 6, 8, 10, 12. Well, what I'm going to do in list 3 is I'm going to type 2 times L1 minus 3. I'm going to take my inputs, my L1s, and I'm going to subtract 3 from them. And so when I put this into L3, this list right here is what happens. And what I can do is I can start investigating what's going on in these two lists. If I look at list 2, the 2 happens when x is 1. When I look at L3, when does the 2 happen? It happens when x is 4. This 2 that's in L3 happened 3 units later. That's so cool. The 2 over here happened 3 units later. In the parent function, the 2 happened at x equals 1, but in the transformed function, the 2 happens when x equals 4. In fact, if you look at that even further, you can look at a list like a table like Leo was showing you a moment ago. And in this table, look what's happening here. 0, 2, 4, 6, 8, 10, 12. These are all my y1s. And my y2 I can see is 2 times x minus 3. Look at all of these y's that are happening here. All of these y's are happening 3 units later. The 0 produced a 0. The 3 produced a 0. Everything is happening later. So what is the answer? When we subtract 3 from the input, the output values occur later than they do in the parent function. For example, x equals 3 in the new function produces the same y value as x equals 0 in the parent. In other words, it happens 3 units later. All y values are happening 3 units later. And so it's a way that we can use the calculator. This part right here, we would explore that with our students. Leo and I didn't have the time to explore that with you today, but we wanted to show it to you so that you could see that there is yet another way that you can use the calculator as a tool for helping kids to understand the math. And so the final challenge that we have is this. I go back to share my screen one more time, forgive me. But what if we had a real world problem that involves both piecewise functions and transformations of functions? Suppose Leo wants to put some stuff in storage. Leo knows a couple things. He knows he needs storage, but what he doesn't know is he doesn't know how long he's going to need it, but it's going to be for several months. Fortunately, in Leo's neighborhood, there's a storage facility that charges $100 for a month per unit. But right now they're trying to drum up some business. So they're going to give you 50% off for the first 3 months. So the challenge to ask is, how can we represent Leo's total cost as a single function? So again, this is a really, really nice investigation with our students. But what I'd like to share with you, Leo showed you the piecewise template. Let's take a look at this Y1 right here, and let's see if we can understand what's all happening here. Well, I know if the cost is $100 per month, and if they're going to give me $50 off, 50% off for the first 3 months, that means the first 3 months are only going to be 50 bucks per month. So hence my 50x. And it goes from x equals 0 up to x equals 3. But then what happens? Why is all of this stuff going on down here? What's that 150 from? Well, that 150 in the second, remember, this function is representing his total cost. So Leo, over his first 3 months, accumulated $150 in his expense account because he had to pay for those first 3 months before this second piece started kicking in, which is that $100 a month. But why is it x minus 3? Because this rate is happening 3 months later. Isn't that cool? So the rate happens 3 months later. So that's where that 100x cuts in. That 100 times the monthly rate doesn't happen until the 4th month, right? And so then we can see over here is that table of values. And so this is a way that we can use the calculator to kind of support the understanding of why that transformation takes place, why it shifts to the right, but it also there is in the context of that piecewise function. And so with that, Mike, it looks like we've taken it up right up to the wire. So I guess we're going to turn it back to you and let you finish this thing up.
Sounds good. I was hoping that you would.
We got a calculator to give away.
That's right. That's right. So speaking of calculators, in case you didn't know what is permitted on what tests now, things sometimes change. There's a quick snapshot that'll be in my PowerPoint in case you want to see this again. It's also available on our website. But as Dave mentioned and reminded me, we are giving away to one lucky winner a TI graphing calculator of their choice. I think Leo's hoping that they pick the 84, but it doesn't matter. They can pick whatever they want. Tonight's lucky winner is Shannon Evelyn Beatty. So congratulations, Shannon. I'll be reaching out to you soon to get some information from you. So look out for an email probably coming tomorrow, Shannon. To receive a certificate of attendance along with a link for the documents that Leo and Dave used tonight, go ahead and click the link coming in the chat window. And if those links aren't working for any reason tonight, just hang tight. Again, you'll automatically get a follow-up email, which I think is going to be super important with all the information that Dave and Leo shared tonight to be able to watch this on your own at your own pace. Again, I was taking notes and I need to go back and wrap my head around some things as well. So it was good stuff. Be on the lookout for a follow-up email that, again, will have links to the certificate, the recording, and the documents as well. And if you're watching this on demand, copy that link into your favorite browser to receive your certificate.
Thank you, everybody. I know it was a lot, but I hope we gave you some ideas that you can think about. And you can always contact us if you have any additional questions.
For sure. And speaking of contacting, we're also here to help. If you have questions about downloading an app or loading an app or sending files out to your students, anything, let us know, 1-800-TI-CARES, or drop us an email, ti-cares@ti.com. We'd love to hear from you. Last but not least, whenever you leave the webinar tonight, you'll automatically get a follow-up survey, which will contain some questions for you about how things went tonight. But most importantly, at least for me, what would you like to see that you haven't seen yet? Is there anything that you think, man, I wish we did a webinar on AP Calculus? Well, hey, that's coming up next week. So be on the lookout for that. But please let us know what we can do to serve you better. Huge thanks to Dave and Leo for everything they shared tonight. The documents, again, I looked them over already. They're really, really good. The screenshots are super helpful. So thanks to the two of them for putting this together. Most importantly, thanks to all of you for coming tonight. This, I know, is time, and I don't want to let you go without saying that we appreciate that you spent some time with us tonight. So thank you so much. We hope to see you back online next week while we're talking AP Calculus, specifically the AP Calculus exam and what we've learned with two really great instructors as well. So thanks so much. Have a great night, and we will see you hopefully next week. Bye.